All right. Thank you, everybody. It is tough to say, but we are in 2025. This is the January 25 installment of the Microsoft Data Platform Business Continuity Virtual Group. With me today is old friend, absolutely amazing guy. It's Andy Yoon. He is a field solutions architect over at Pure Storage, doing some really cool stuff with a lot of really big toys. And with that, I'm going to pass this over to him to talk about accelerating your database backups.
Great. Thank you. Thank you so much for joining me, everyone, today. And thank you for having me here at this virtual user group. And welcome to Accelerating Your Database Backups. Just a quick bit about me. I'm a field solution architect at Pure Storage, but really the important thing to understand about me is that I've been a SQL Server DBA and DB dev for a very, very long time. Been working with SQL Server for quite a while. Used to be very active in the Chicagoland area, but I'm now based out of the Boston region as well. SQL Beck is the one key thing to know about me or to remember about me. That's my online alias, but that's also the key to finding me, whether it be on any of the different social platforms these days, although I'm not as active as I used to be. But of course, you got my email address. My blog is off of sqlbeck.com.wordpress.com, and also my GitHub, which happens to have code and a copy of this particular presentation as well. My spouse is also the amazing Deborah Melk, and she's also another data platform community speaker and MVP out there. So go check out some of her sessions. And then we have our dog, Sebastian, who may or may not make a few cameo appearances during this particular presentation. All right, so database backups. And how many people have ever heard quotes like this one? Oh, this database isn't all that big. This is only ever going to be this large in size, right? It's never going to get bigger than just a few gigs, right? We've all heard that type of statement. But here's the thing, especially in today's day and age of 2025, which terrifies me to say, data volume is growing at not only just exponential rates, but whatever the next tier beyond exponential happens to be. I'm obviously not a math guy. More time that passes, the more data volume gets generated. We are generating a tremendous amount of data volume right now as packets are flying over the internet, as you're watching me stream live over the internet, as this is also being recorded. All sorts of things are happening every single second that passes in our lifetime from a data volume perspective. Someone is generating data, and that someone also includes you and your databases. Well, I certainly hope that, if you're at this particular presentation, you're also taking backups of your databases. But unfortunately, as Sebastian is letting us know here, not everyone does. Even in today's day and age, I still encounter customers that don't take regular backups of their databases, and that's also a problem as well. But assuming that you are taking backups of your databases, one of the challenges that we happen to face oftentimes is juggling business priorities. We don't necessarily have the luxury of taking full backups all the time, like say every single day. For example, we have to juggle those different priorities. We also have to juggle the business risk of not having frequent enough or appropriate backups based upon our RPOs and our RTOs versus what kind of maintenance window we may happen to have, especially as our enterprises get larger, our data volumes get larger. Oftentimes, our maintenance windows will conversely get smaller and smaller. So managing those databases and how your database backups, how often you can take them in regards to your priorities for data protection, is very much a juggling act. But what I'm here to do to help you today with is to hopefully teach you about some ways that you can accelerate your database backups so that way you can get some of that time back. And, from Sebastian's selfish point of view, he can get some more doggy walks so that way you're not sitting there staring and managing and juggling your backups. So, to that end, here's today's agenda for this particular presentation. For the next 60 minutes or so, I'm going to briefly talk a bit about backup internals. And then we're going to talk about some different backup-related data transfer tunables. These are specific parameters that we can tweak and play around with in order to try and accelerate our different database backups. And then I'm also going to touch upon SQL Server 2022 and one of the new capabilities that brought to the table that I find very interesting and compelling in regards to backups. I also want to be very clear. There's a couple of topics that I will not be covering in this particular presentation. Particularly, we will not be talking about restore capabilities, nor are we going to be talking about different backup strategies. How often should I be taking a full versus differentials and T-logs and things of that nature? Backup strategies, HA and DR strategies, is a whole entire presentation in of itself. Today, we're just going to focus on the code, on the actual backup in of itself and accelerating that. Okay? So now that we've set the agenda, let's dive on in. Chapter 1, Backup Internals. In the context of a backup operation, we have a number of different players. Of course, we have the backup file or files that are being backed up. And then we have the backup files themselves, the target that we are writing out our data to. And then we have the operators or the actors, if you will, who are doing the work. We have CPU threads, reader threads, and writer threads that are both reading from our data files and writing out to the backup files. And then finally, we have what I like to think of as them passing around boxes or buckets. These are backup buffers. And this is what they will basically throw our data into as temporary containers to pass them back and forth as we write data, as we read data from a database file and eventually write it out to a backup file. So how does this all work together? Let's kind of take a look at this diagram. And we have a couple of different animations here. On the right-hand side in the purple here is our backup device or file. A device is more of a generic term or a generalized term, but we are backing up to a file in most cases. And then on the left-hand side, I have a cylinder here that represents the database volume. Key word here, this is not representing a single database file. You may have one or more files on a given volume, and a volume is oftentimes represented as like a drive letter in Windows, for example, or you could be using mount points, but this is the disk, essentially the LUN that is presented to your server. Why I specify volume here will come back to haunt us in a little bit. But for now, just understand that this diagram is showing us a volume that contains one or more database files on that volume that we're backing up. And then this box here happens to represent the backup buffer. And then at the top, we happen to have what are called the free queue and the data queue. These are just collections of one or more buffers. In this case, this is the simplistic example where we just have a single buffer. And then we have a reader thread represented by this arrow on the left-hand side that is reading off of that database volume and filling our backup buffer up with some data. And then once that backup buffer is full, think of it again like a little bucket that I may have. You know, I can't take the entirety of the database unless it's a really, really teeny tiny database. You're just going to fill up this bucket full of some stuff. And then once that backup buffer is full, it gets pushed off of the free queue into the data queue. And then once it's on the data queue, the writer thread is sitting there watching the data queue and says, oh, I now have a new backup buffer with some data on it. I'm going to consume that backup buffer and write it out to the backup device or backup target file, therefore draining the backup buffer, freeing it up, and allowing that backup buffer to be passed back to the free queue. This is fundamentally the workflow of a backup operation underneath the covers. But of course, it's not just that simple, is it? So there are different variables that we can play around with here. So what if, for example, I were to add in more backup buffers to this entire operation? Well, understand that the reader thread can only fill one buffer at a time. It's a serial operation underneath the covers. So you'll watch my reader thread fill, move, fill, as these backup buffers are being then transitioned from the free queue to the data queue. And asynchronously, essentially, the writer thread is then watching that data queue and then, consuming the filled backup buffers and then writing them out to my backup file. But it is also a serial operation as well. Each thread can only work against one backup buffer at a given time. Okay, so what happens if we add more backup files? This is where things get interesting. So I still only have one reader thread on the left-hand side. However, for each additional backup file or backup device or backup target that we add to our backup operation will give me another writer thread. So now instead of one worker on each side, I now have three workers available to me on the writer side. So in parallel, I can consume and write the contents of three backup buffers simultaneously now. So now we have a little bit of parallelism, and parallelism in this case is a good thing. Now, this is where I made the big point about the data files and data volumes. Microsoft, in their wisdom, for whatever reason, has tied the number of reader threads to the number of data volumes that your database resides on, not the number of data files. So you could have a massive data warehouse that has, like, maybe you've split it out into 10 different data files over the years, but if they all still reside on the same data volume, your backup operation is only ever going to get one single reader thread. In order to get more reader threads to the party for a backup operation, you must take those data files and spread them across multiple data volumes. In this simple case, I'm just going to add another data volume. We'll call that the E drive in this simple example. And now I have two reader threads that are now available to me. Oh, and I forgot I added a third one. So we now have three. So three reader threads can now simultaneously hydrate three backup buffers at the same time. So I have some parallelization. Yay. But in this example, we still only have one backup file. So therefore, it's just one writer thread. So I can only consume the backup buffers in that slower serial fashion. So if I advance all the way to the end, and if I have equal numbers of reader threads and writer threads, that gives me a good amount of parallelization here, okay? Yay, and we like parallelization because that means that, of course, I can do, I can process more data simultaneously, and I can write more data simultaneously. Now, in most cases, though, you're going to have kind of an unbalanced scenario that might look something a little more akin to this. Maybe you've been able to take your database and put them across two data volumes, and you're going to have more than, more backup buffers available to you, of course. So this is what a typical backup operation is more than likely going to wind up looking like. Where do you hydrate, those backup buffers and so on and so forth, and they kind of get passed back and forth in a somewhat jumbled fashion, depending on how fast you can read and how fast you can write, depending on the number of reader threads and the number of writer threads you happen to have. And also keep in mind that this diagram does not account for the amount of time it takes to read to fill a backup buffer. So you're reading from your storage subsystem, and the amount of time it takes to write for a writer thread to write across your storage subsystem as well. Because oftentimes we are reading from one storage subsystem, maybe local direct attached storage, but we're writing out to somewhere else, like a SMB share on another file system, further out there in the network. So now instead of reading, I read locally, but I write, over the network, for example. So there's, of course, going to be different time differentials involved there. This diagram, of course, does not portray that, but understand this is more just to illustrate the work that's happening from a more discrete perspective of the relationship between the backup buffers and the different threads, the reader threads and the writer threads. Oh, I jumped ahead of myself. So yeah, some of the other factors to consider is the source disk read capability. How fast can we read off of disk? Because we can never accelerate our database backup any faster than the read speed that we are capable of. There's, because if I can't, hydrate those backup buffers, or that's the max possible speed that I will ever be able to achieve. I can't somehow write faster than I can read from my database files. And of course, we are resource constrained because, of course, we happen to have CPU and RAM that needs to be available in order to do all of this different work. And then I already touched upon the whole target connectivity thing about, what is the storage interconnect look like? What does the latency look like? What kind of throughput do you happen to have available between the backup target and, your particular SQL server in question? And then the target disk write. So whatever media or storage subsystem you happen to actually be writing to, of course, has its own write latency. How fast can it consume I/O? So that's a bit about the internals here. Now let's talk about the data transfer tunables. So what can we tune? Well, we've seen from the diagram that, and the animations from the prior chapter, that, the things that we're capable of tuning, the practical things that we're capable of tuning, keyword there, are the number of CPU threads in the party, the number of backup buffers we happen to have available to us, the size of the backup buffers, which could also potentially be very useful to us as well. Okay. So CPU threads from the writer perspective is the most easiest, in my opinion, to manipulate because it's easy just to add more backup targets. Many of us we call the term backup striping, where we will write out to multiple backup targets, backup striping. I keep getting ahead of myself here as I'm thinking about what I want to say. And then on the reader side, I already kind of hinted that, we do need to add more logical volumes. And I don't know about you all, but me and my role at Pure Storage, I've been begging product to divorce or, get rid of this whole, connection to, reader threads and the underlying volumes. We've been begging them for God knows how long to, make this a tunable parameter in of itself, or tie it off to the number of data files instead of data volumes. But it's obviously very, very low if ever going to happen on their priority list. So that's life. So you do need to add more logical volumes if you want to bring more reader threads to the party, and that is typically a non-trivial effort. Depending on your storage subsystem and your SAN, you may have some interesting capabilities to enable you to do that in a slightly easier fashion. But even with capabilities like what Pure brings to the table, sorry, I don't mean to keep bringing up Pure, it's just a simple reference for me. But what certain SAN vendors bring to the table, like if you were to use snapshots and stuff, there's still some downtime that's going to be involved. Is really the point that I want to kind of, bring to the party here. It's not always practical to be able to do that. And you do have to be careful of the physical infrastructure, whatever your SAN subsystem is, but the vast majority of folks out there are also virtualized these days. So there's also additional considerations that you need to think about if you're going to be adding in a whole bunch of additional volumes to a given SQL server. Now, to tune the number of backup buffers, that's also pretty easy as well. There's a parameter in the backup operation called buffer count. Okay, cool. So if you don't specify buffer count's default happens to be this really ugly algorithm and formula here that's tied to the number of backup devices, plus what's documented as the suggested I/O depth, which happens to have a couple of different hard-coded values depending on what your backup target type happens to be. Almost all of us happen to back up to disk as opposed to, say, backing up to URL. So the default for backing up to a disk backup device happens to be the number 3. And then the number of database devices, or in this case, the number of database volumes. So that all comes into play as well. If you're using pure defaults and you're just doing a regular old just backup database and pretty much specifying nothing else, you will use 7 backup buffers. That's how many you're going to get. Well, how large are those backup buffers? That's what max transfer size, which is our final tunable, will define. Max transfer size can be anywhere from 64 kilobytes all the way up to 4 megs, and its default size happens to be 1 meg. So we're going to be using 1 meg IOs in this case. Think of it as a box. It's a box that can fit 1 meg worth of data, as opposed to a smaller box that could be 64 kilobytes worth of data, or a larger box that could be 4 megabytes of data, for example. And if you're tied to using TDE, VDI, and/or if you're writing out to tape, then the max transfer size will be a different value. The default size of 1 megabyte happens to be for disk, and again, without those different caveats in that particular case. Otherwise, that will have an impact. So remember, these backup buffers exist in memory. These are memory buffers after all. So the amount of RAM that you will need in order to execute your backup operation is very simple. How many buffers are you allocating, and what is your max transfer size? And this is assuming no compression, by the way. Compression is a separate topic. We will get to that one later. So in this case, most simplistically, that's the amount of RAM that you will need. This is a separate this is a separate memory allocation beyond the buffer pool that we typically think about when, as far as SQL Server and memory utilization is concerned. So this does not come out of the buffer pool. This is something extra. Now, for one single backup operation, that's not that big of a deal, but many of us will try and back up our databases in parallel. I've been in situations where I have a SQL Server that's got hundreds of databases on a single instance. So I'll, set up multiple jobs, like 5 jobs that will, maybe tier out my databases or just assign them to different groups. So that way, in a given maintenance window, I can be running 5 backup jobs simultaneously. But of course, with each simultaneous backup job that happens to be running, that's more RAM than I'm going to need on my given SQL Server. So in either case, hopefully the key takeaway here is to be mindful of what the physical infrastructure happens to be look like on your SQL servers. As far as how many, threads you happen to have. Maybe if you're a smaller virtualized SQL server, is it just a couple of vCPUs, for example, and, you only have 16 gigs of RAM available to you. And because memory utilization is beyond what the buffer pool is, have you properly accounted for that, especially if you're trying to do 10 parallel backups simultaneously, for example, because all of this will add up, as we will now see in demo, as we start playing with these different tunables and also getting into some fun trace flags that'll get us into the nuts and bolts. Let me pause at this point, by the way, and see if there are any questions in the chat, because I know I've been talking a lot, about the internals and stuff.
So far, I think we're good. If anybody has any questions at all, do not hesitate. Throw them in the chat window and we'll get them answered.
All right, yeah, and I do have the chat window up here, so feel free to also, make some commentary in the chat. I should have mentioned this early on. I enjoy, a little bit of interactivity and such. So if you want to jabber at me in the chat, I will most likely respond. Okay, so we got a couple of demos here. So first of all, I want to show you what we're going to be working with. I have 2 databases here called Sandbox Small with slightly different variations. These are both multi-file databases, but one exists on a single volume and one exists across multiple volumes. First of all, from a totals perspective, they're just shy of 20 gigabytes in size. I had to try and keep this fairly small so that the demos and the backup operations would actually complete in a timely fashion in the context of, this particular presentation, right? Y'all don't want to be sitting here for 5 minutes at a pop watching me run a backup, right? So let's look at some underlying details. So this is just a variation query that's looking at sys master files. So that first database, Sandbox Small, multi-file, single volume, all exists on my M drive here. Okay, so it's 4 data files. Otherwise, the multi-file, multi-volume, its data files exist on different drive letters here, or different volumes, the I, J, K, and L drives here. And you see that we got the T log here sitting out on the Y drive. That's not really relevant to today's conversation, so not worrying about that. Okay? So let's take a quick baseline. So this is where I want to introduce the concept of using something called disk equal null. Remember, I made the point earlier that your backup operation, the best performance you will ever get is tied to the read side of the entire operation. So what disk equals null does here is that it will essentially throw away your underlying data. You will never write out to your backup target. There is no backup target that's being specified here. So this is a way to measure what is the best possible effective throughput that you will ever get on a backup operation. So in this case, I'm just doing disk equal null, one single backup device, no other tunables here, just to get my true baseline. And we're going to do this against the single vol database and the multi-vol database. This should take about 10 seconds or so for both databases. And let's make some observations. So the first database, the single volume database, took about 8 seconds. And this throughput value is the effective throughput, not just the raw read throughput. You'll see that there's other things that can come into play, but this is what we effectively had during the course of this operation, just under 2,000 megabytes per second in this particular bit of storage. So that one took about 8 seconds, single volume. But interestingly enough, if I scroll down here, the multi-volume one was a heck of a lot faster, 1.3 seconds, even though, and my effective throughput was a bit higher, about 23,000 megabytes per second. So that's pretty cool. But look at the duration. This is what's really, really, really tremendous. And, okay, I must apologize to everyone. I just realized something, that I have a little bit of a problem with my demo data here. I had increased it. So, okay. I had increased the size of multi-file single volume here, and this query up here is showing what is allocated, what is provisioned as far as the database files are concerned. But I just realized something. This is actually showing me the number of data pages that are backed up. And this one here is actually a lot less smaller. So I think I actually completely goofed here as far as pre-staging and pre-setting up my underlying databases. So that's going to have a little bit of an impact on the underlying subsequent demos here. So I'm just going to have to talk through a few things. This is terribly embarrassing, but hey, stuff happens. I do apologize, but we'll make this work nonetheless. So, all right. In either case, we're just going to now work off the single volume. Yes, thank you. Sorry, y'all. But I appreciate the supportive statement, David. But all right.
Look, I'll break in to be comic relief here, man. The demo gods have struck. You're perfectly fine. This is
Right.
about the
In
most
either case,
laid-back group you're going to find. You're
right.
perfectly fine. Stuff happens. Don't worry.
Yes, and I can at least explain what we would normally be seeing once the two database files are of equal size, of truly equal size. And we'll still get a good sense of that, even though the multi-file database obviously happens to have a lot less data volume. It just won't be nearly as drastic, but it'll still be somewhat drastic. But we'll run some of these other subsequent backups with just a single volume one here. So this is where basically I'm, just kind of showing off. Will this actually improve our backup operation here? So I've added disk equals null, but 4 now. So there's 4 backup targets, even though I'm throwing away everything, because there's still 4 backup targets. We still have 4 writer threads that will still throw away 4 backup buffers worth of data instead of 1 backup buffer worth of data, which is why my backup operation was still able to decrease in execution time from that original 8 seconds or so to about 5 seconds or so. And of course, with the multi-volume, you would have seen a similar sort of drop in execution time and an increase in performance. Notice the effective throughput has also increased as well. Now I'm going to go back to disk equals null, a single disk equals null, but now I'm going to crank up buffer count instead. Will we see an improvement there over our original baseline? Of course, the answer is, once again, yes. My execution time has also dropped, because even though I've kept it to a single reader thread and a single writer thread, I now have more backup buffers in play. And, in the case of using like 150 was just an arbitrary number I happen to choose, that reader thread can fill a lot of backup buffers really, really, really fast. And that writer thread, even a single writer thread, can also consume them really, 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 really fast. Now, mind you, this is a fairly powerful SQL server that I happen to be running on. If you're on an older, crappier SQL server, or maybe a SQL server that's under a lot of stress and duress because of shared workload, your reader threads and your writer threads may be more constrained, may have some more challenges as far as how fast it can process a given backup buffer. And we'll see a little bit about that shortly with wait stats. But first, what I want to kind of show you are 3 different trace flags. So 3213, 3004, and 3014. Those 3 combined will give you all sorts of different levels of information about what's going on behind the scenes with a backup and restore operation. In my various research coming up with this particular presentation, you'll see this in the resources slide later on. Exactly what is presented in each one of these is not really deterministic. There's kind of some inconsistencies that are presented out there, and it also seemingly has changed over SQL Server versions. Therefore, to be comprehensive, I'm going to turn on all 3 of them. So we turn on all 3 of them, and then I'm just going to use 3604 and 3605 to redirect information to the Messages tab. So now let's get a glimpse of what's really going on behind the scenes with our backup operation. First, we're just going to run multi-file single volume here. So inside the Messages tab, we have information about SQL Server taking our locks, for example, and we're opening up our backup media set. We have information about the memory limit that we happen to have set on this machine versus the buffer count, the default buffer count. Remember how I mentioned that earlier? So it's reporting that. How many sets of buffers do we happen to have? We only have one set of buffers, so 7 buffers total. The idea of a set of buffers will come back into play. Well, actually, if you use SQL Server compression, you'll actually get multiple sets of buffers, 3 sets, because you have the read set, the buffers that then get utilized for compression purposes, and then the write set there as well. So you're going to have more memory utilization, which is one of the trade-offs of using SQL Server compression. Max transfer size is the default of 1 meg, and then total buffer space was, again, just that simple calculation, but we have all of this information available to us here. Some of the other interesting tidbits here, we see information about LSNs. If this was a highly transactional database, you might see some different LSN information here. Effective options, I have compression turned off by default on the SQL Server instance, so we have that confirmed. I'm not using TDE because TDE is evil. That's a side topic. Sorry, I'm going to throw that in there. What were some of the other tidbits in here? So we're writing some of the different metadata, but this is actually really cool just to see these are the different things that SQL Server is kind of coming up with. Calculating expected size of total data. One interesting behavior underneath the covers is that SQL Server will make an estimate as far as how large it thinks the backup file or files will be in the end, but it may actually be a little bit different depending on compression utilization. So what some people have observed, and I've had some conversations with folks on like Reddit and stuff, is that why does SQL Server, when I start the backup, it'll allocate 10 gigs to those backup files, and then once the backup operation is completed, that it'll then drop down to like 6 gigs or 7 gigs or expand out to 12 gigs. It's because SQL Server is making this estimation, pre-allocating the space, and then afterwards, oh, I didn't need as much, or actually I wound up needing more, right? So that's why you see that particular behavior. And this is the other line that I also want to throw out here. Number of data file readers. In this case is 1 because we're only against single volume. I'll run this again for multi-volume in a moment and you'll see how this differs. And now we see the messages that we typically see, which is the stats output. In this case, I just use stats 15. And now we have some more information where we recalculate the sizes and make some different changes. And then we do the tail of the log type operations down here, look at the differential bitmaps and do any work around that. There's more file sizing type information, blah, 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 blah. This is where the LSN stuff is happening, and so on and so forth. But now the backup operation is finally completed. But this is a whole slew of really, really cool, extra nerdy information, internals information that I really enjoy. I'm just going to quickly run the multi-file, multi-volume version. Remember the number of devices, number of database volumes was part of the calculation as far as determining the default number of buffers that will be needed. That's why buffer count is now 13 instead of 7 here, because we have, this database is across 4 different data volumes. And if I scroll down to the reader portion, number of data file readers, 4. Okay. So a little bit of differences there. And remember, this is the underlying calculation here. So if you're looking at these scripts a little bit later, maybe playing around with this in a staging or a dev or a QA environment on your own, you can play around with some of this and see that information and see how your backups are operating today. And you can have this handy. Okay, so we've taken some baselines. Now let's jump into actually working with some different tunables here. So that's demo number 2. See, I'm debating if I should just skip the multi-file, multi-volume stuff, or, we're just going to roll with it here. Because there will still be deltas that I can kind of show you here, even though the data volume is a bit smaller in the multi-file, multi-volume version. Okay, so we've taken our different baselines here, and I'm going to record some information here. So our buffer count is 7, max transfer size is 1024. Total buffer space is 7 megs. I need to grab the effective options. Come on. I'm going to grab that out here as well. I already know that the number of data file readers happen to be 1, but the most important thing to eventually grab here is what our effective operation happened to be. So about 8 seconds or so, and up just under 2,000 megs per second. And even though this database is a bit smaller, we can still, again, glean some interesting things out of it, like, buffer count being, 13, max transfer size, at 1 meg. So, we used 13 megs worth of buffer space. I'm going to leave that alone, and we know this is effectively 4. But our effective throughput, even though we backed up less volume of data, was still higher. So we really can't look at the execution times, but we will at least look at the effective throughput there. All right. So now let's actually do a backup. In this case, I'm going to be backing up to an SMB share against, one of my other devices. So we're reading from one storage subsystem and writing out across the network to a different storage subsystem. So it's not the same subsystem. Like if I was doing this on my laptop, I'm not reading and writing from the same hard drive. That's actually one reason why I'm doing this in my work lab as opposed to on my hard drive, because if I was doing it on my hard drive, I actually run into other contention issues, and it doesn't make for very good demoing. So that's why we're here. All right. So single files, multi-file, single volume to single backup file output versus the multi-file, multi-volume. And I've turned off the trace flags for now because we don't need the extra diagnostic information. Now, this is where my effective throughput really, really drops, because now I have to worry about actually writing that data out across the wire. This also could be a case, because this is a shared work lab and I have many colleagues that are doing stuff. They could also be saturating some of the other devices that are on out there. This is much more representative of what might be happening in a real production environment. But we've now dramatically dropped down what my effective throughput happens to be, 700 megs per second. And then for the other example, is about the same as well, around 700 megs per second, okay? So, that's a great question. Why wasn't the multi-file faster here? We have more reader threads. I would have expected this to have been a bit faster from an overall effective throughput perspective. And this is where we're going to look at wait stats. So what I'm going to do is I have a variation of Paul Randall's wait stats script here. We're going to kick off a backup, and then we're going to run, we'll kick off a backup, and then we'll run this to see what the cumulative wait stats happen to be. No one happens to be on this server right now, so I'm actually going to flush the flush all the waits for the instance, and that way we'll have fresh information. But we're going to be looking after a handful of different backup-related and/or I/O-related wait stats as we go through this process to see what is SQL Server waiting on during the duration of this. Why was my performance just kind of plateauing off in that single backup file scenario? So we're using this dbcc command to clear wait stats. Please be very careful about ever running this in a prod or non-prod environment, because you're wiping out all wait stats. And then we kick off the backup operation. We're just going to use multi-file, multi-volume here, because again, we want to answer, even though I happen to have more reader threads, what were we waiting on? Could I have made this even faster? Because we only got about that 700 megs. But according to the wait stats, the primary wait stat that we incurred during this period of time is the backup buffer wait stat. What does that mean? Well, I have this handy set of code here to cheat. A reader thread was waiting for available empty backup buffer. Remember, we only ran with the defaults otherwise, so I only had a handful of backup buffers that were available to me. Remember, I tried to make the point earlier that a given single thread can read into or write out of many, many buffers, even though it's serial, pretty damn fast. So if I only had, 7 or 13 available to me, that reader thread can still fill up all 13 pretty damn fast, and then it's going to be sitting there and waiting. So this is a case where we should be able to get better performance if I were to increase buffer count without increasing anything else. So let's follow the same workflow. I'm going to flush out my wait stats, and then I'm going to kick off that multi-file, multi-volume backup with a buffer count equal to 500. And my effective throughput has increased a little bit, not a huge amount, but it did increase some. So that's honestly kind of what I expect. And let's take a look at the wait stats and see how it differs from this. Also keep in mind the volume or the total amount of waiting that occurs. So this is, again, a cumulative value, but we'll just look at the relative numbers, 18, 4, and 5 here. Now these numbers have dropped. So that's good. My reader thread is still waiting every now and then, but is not waiting nearly as long. Not the 18 that we saw earlier, 13. So a little bit of an improvement here, even though I brought in more, more buffers to the party. So in this case, I'm going to crank up buffer count way, way, way much higher to 2,500, which of course is going to utilize more RAM. Now, this is me, of course, going to another extreme. And remember, this is a very, very beefy server. I've not really increased my effective throughput all that much in this particular case, but my overall volume of weights have reduced. So, and even though backup buffer happens to be the very first one, I now have a couple of others that are in play here, and the overall values of them, the volume of weight that we are actually weighting, has also decreased on overall in the grand scheme of things. And keep in mind, this is a very small demo database. Think about what these numbers would happen to look like against a multi-terabyte database as opposed to something that's less than 20 gigs in size, right? So this is something where you'll see much greater rate of return. But the point of this is that only increasing buffer count and not affecting anything else will only get you some nominal savings. We need to work with multiple tunables simultaneously. So buffer count alone in this example didn't really help all that much. And I'm not resource constrained on the SQL Server either. So let's take another variation. I'm going to use the multi-file, multi-volume. So we have 4 reader threads available to us. I'm going to use buffer count to 500. But now I'm going to bring 4 writer threads to the party. Let's see how this helps. Wow, this executed a heck of a lot faster. And now look, my effective throughput is now through the roof. This is great. This is why I was trying to get to the point of, just changing backup buffers will only give you a nominal improvement. And the total volume of waiting that we had to do also decreased just a little bit more. So now we're hitting a point of being even more efficient in our relative backup operation and improving our effective throughput. This is great. Now, what happens if we start playing around with different I/O sizes? I've changed max transfer size to 2 megs instead of 1, keeping buffer count at 500. About the same execution time as the execution before, about the same throughput. Let's take a look at the weights, see if weights differed. This is around 3.9, 3.4, blah, blah, blah. And in this case, this is about the same as well. The moral of the story here is that depending on the size of the database and your underlying hardware, you'll see a diminishing rate of return, okay? That's where I'm really trying to go with all of this. But if I now increase the number of threads, once again, we only have 4 reader threads, but I'm going to increase the number of writer threads to 7, with max transfer size being larger and buffer count being larger. I've increased just a little bit more, and you would actually see a much more drastic improvement if this was a much larger database, is the what I would be telling you if this database was a bit larger. Again, nominal improvements, but at this point, we're not shaving off 20, 30, 40%. We're shaving off 3%, 4%, 5%. But even those single-digit percentage improvements do add up over time at scale, especially when you're talking about a multi-terabyte database as opposed to something different. And I can also max out max transfer size if I wanted to, and or really, really jack up buffer count in the interest of time. I'm just going to do, I'll just do this one just to kind of prove the point here. Hey, this is a really beefy server. I'm going to increase both max transfer size and in this case, increasing buffer count and max transfer size, I actually had a decrease in effective performance here, which is kind of interesting. Again, it's the moral of the story is you don't want to just shoot for the moon here. The more resources you throw at it, just like throwing more hardware at terrible code, you're going to get a diminishing rate of return, is the moral of the story here. All right, cool. So with that, let's pivot back to the presentation and continue onward. PowerPoint, where are you? There you are. Those buffer count sizes seem big. How high can you go before you start seeing issues elsewhere in the box? Great question. Yes, they are really big, but that was a very large bare metal SQL Server that I was happening to use. Again, just to show extremes, in the other end. Use those trace flags to see how much RAM is actually being burned down, especially if you are or are not using compression. So, if you only have a 32 gig machine, you're going to be burning down your RAM really, really fast. Another trade-off of all of this. So very, very good point. Are those trace flags safe to enable in production, or should they be enabled with Microsoft support? Technically, they're pseudo undocumented. You'll see some information about that. I think it's on the next reference slide here. It's on one of the reference slides, but I don't know if they have been pseudo documented by Microsoft. It just generates additional output data, but it's not like an extended event or anything else underneath the covers. So use caution, I would say, because I can't give you a definitive answer on that one. But, for all intents and purposes, it should be no more harmful than, just any other trace flag that just outputs additional volumes of data, to my knowledge. Okay, but in either case, this reference information, don't forget SQL Beck, my online alias, and github.com. All of this information is there. Now, this is actually a really cool utility that Nicholas Kane wrote a number of years ago. It's a backup test harness that will basically execute backup statements and permutate through, all different values, so that way you can get a better sense of what works well on your system and your environment with your databases. So check this out. It's a really cool utility. I use this for some backup testing that I've done, over the years on some of our hardware. So it's some cool stuff. And yes, Chris made a comment about, upping the buffer count one day and bringing down instance. Because remember, it's its own separate set of RAM that it needs in order to execute that backup operation. And it'll take all of it. It's not like I can say, oh, I needed 500 buffers, but I only have enough RAM for 200. No, I'm going to grab all 500 buffers. So it's all about, as Sebastian here says, the moral of the story is we must strike that balance. Okay, so hopefully the demo kind of gave you a good sense of that as well. So what does SQL Server 2022 bring to the party? It brings to the party a new way to compress our underlying data. Now, first of all, should we even be using backup compression or not? Generally speaking, I say yes. Mainly because we will then wind up sending less data over the wire to our backup targets at the cost of CPU utilization. So backup was originally created in such a way to minimize CPU utilization and minimize resource utilization with all defaults. Of course, we can change that and crank things up. But if I now add backup compression into the party, we will now see CPU utilization jump up dramatically, because of course that CPU must be utilized to take your data, squish it down before it writes it out. So the trade-off here that we sometimes have to think about is how much data are we backing up? These, again, databases that are just in the gigabyte size range, or are they in the terabyte size range? When are we happen to be doing this? Do we, is our workload such that it's a 24/7 workload, or do we have the luxury of having many hours in the middle of the night to do our backups willy-nilly, and we have the entirety of the server's resources at our disposal? Because I don't really care, because nothing else is going on. I'm also not running other maintenance simultaneously, so I could burn down that CPU. And then again, you need to worry about, where are you backing up to? Are you backing up to a direct attached storage, a local disk that maybe you have another third-party thing that's scooping up and archiving somewhere else? Or are you backing up over the network into a shared space, maybe an old legacy SAN, in which case it might be in your best interest to minimize the volume of data that's being sent over the wire? Because maybe you have 30 SQL Server instances that are all trying to back up to that same old school SAN, for example, and you don't want to oversaturate that. So that's some extra math you have to do. So what SQL Server 2022 does is it brings a new compression algorithm to the party called, and this technology is all bundled in and called Intel's Quick Assist, or Intel QAT. So you have two options to embrace this, or to take advantage of this. First is hardware acceleration. Use QAT is built in. So cool, it already is available to you. On older servers, you can get a QAT card to slap into one of your servers, and it'll offload it to a hardware card. And these cards have been around for many years. So keep in mind, even though this was only introduced in SQL Server 2022, Intel QAT has been around many, many, many more years prior to that. So SQL Server and Microsoft just added in hooks to be able to leverage this particular capability. So you can do hardware acceleration and offload it to a card, or again, newer CPUs have QAT built in straight away. If you have neither, you can actually software emulate this too. But Andy, doesn't software emulation usually suck and still going to burn my resources? And oftentimes the answer is yes. But in this case, what's interesting is that even software emulation happens to be more efficient than traditional legacy compression. And it's available to you in both Enterprise and Standard Edition. It's not tied to Enterprise Edition only. So this is one of those things where you're really going to be able to benefit at scale. So I did some testing early on when 2022 was in private preview to help out Microsoft with all of this. I've actually published a couple of blog posts about this because not too many people have actually talked about this. It's like me and Glenn Berry. But here are the results that I did. So MS Express that you see in that compression type chart here, that is the code name for the legacy compression algorithm. And then QAT deflate is the parameter value that's used, one for software, one for hardware. And you see that even with software compression enable, I'm still able to get some savings from, the size. And even though my CPU utilization is 36% average, it's still a heck of a lot better than 62% on average with traditional legacy compression. And I would much rather get that and also increase or decrease my backup size, the size of my underlying backup files. Because 566 megs written versus 502 or 408. In this case, it actually software QAT wound up being slightly more efficient, which is kind of funny. But in either case, think about those. The execution times, the elapsed times are nominal differences here, but this is again on a smaller-ish database, a 1.7 terabyte database. Think about this at scale if you happen to have many databases that are running simultaneously. This is something that could be really, really awesome. So big differences there. 13% reduction, 42% reduction in CPU, blah, blah, blah. So SQL Server 2022, even though some people have not been a big fan of it, I still strongly say it brings a lot of other things to the party that are extremely beneficial. And QAT compression, backup compression, is one of those capabilities that not a lot of folks have really shown a spotlight on because, frankly, it's not all that shiny. But it's still something that can definitely help us, especially as our data volume just continues to grow and grow and grow. Now, one bonus topic that I'm also going to throw into here as well. T-SQL snapshot backup. Yes, I use the word snapshot and backup in the same sentence. So in the world of SQL Server, before SQL Server 2022, we could take application consistent snapshots of our databases, but those all relied on something called the volume shadow copy service, or VSS. I'm not a fan. I never have been, particularly because VSS is single-threaded and will stun your SQL servers. And because it's single-threaded, if you happen to have a volume that's got like 300 databases on it, the stun is a serial operation. So you could, instead of being, stunned for a second or two, it takes much, much longer. There's other quirks and other things around VSS that make me not very much of a fan of it, but that's beyond the point. And then depending on your underlying storage, many storage vendors happen to also be able to offer crash consistent snapshots. Now, the fundamental difference with an application consistent snapshot and a crash consistent snapshot is whether you can get point of time recovery by being able to apply additional transaction logs to a snapshotted database once you restore it. With a crash consistent snapshot, you cannot apply additional transaction logs. SQL Server goes through crash recovery, and your point of restore is the time of snapshot. And also, some legacy storage out there didn't really do crash consistent snapshots correctly either. Like, for example, if you happen to have files, your database split across multiple volumes, like stuff on a data volume and stuff on a log volume. And you say, I need to snapshot both of these simultaneously because, of course, we need to maintain consistency between data and log files. Some legacy storage would actually still do it behind the scenes serially, not truly simultaneously. It may only be a millisecond or two apart, but a millisecond or two may just be enough for data that's in flight to now get your database out of sync between your data files and your log files. Not good stuff. So check with your underlying storage vendor as far as whether crash consistent snapshots are available. They are on some. One of those vendors may happen to be the color orange, but I digress. In either case, the key thing around snapshots and whether a snapshot can ever be a backup is this. Can you get that snapshot off of the underlying storage? Because one of the key principles of taking a good backup is making sure that it's hardened to multiple sources of media, or essentially you want to get it out of your data center. You want to get it somewhere else, right? So, I'll take a backup locally, but then I'll copy it somewhere else. I'll copy it up to the cloud, to a DR site. I want to have multiple copies of it somewhere. Legacy storage implementations, you were stuck with that snapshot just being, stuck on that array and only on that array. So a lot of us argue that a snapshot could not be a backup. But here's the thing. SQL Server 2022 changes the game when it comes to taking application consistent snapshots. You no longer need VSS is the long and the short of it, because they've now taken that code and buried it inside the storage engine. And so some of the key benefits with T-SQL snapshots in 2022 is that it's fundamentally just a backup operation. So all the history, everything is tied into your MSDB backup tables, so you can see everything that's happening there. The stun in of itself has now truly been minimized. In fact, only write activity is stunned. Read activity is actually not even stunned. So you can execute one of these and will stun your SQL Server for just a matter of milliseconds, at least on our hardware where I've tested it. So, and that's why, that's why this statement is here. It's because, of course, your underlying storage and SAN must still be able to take a hardware level snapshot. But the cool aspect here is that, the application consistent portion of it that used to be relied on VSS, you no longer have to rely on VSS anymore. So this is now something where if your underlying SAN can also take that snapshot and offload it somewhere else, dare I say, a T-SQL snapshot can now become a backup. So imagine a world where you happen to have that multi-terabyte database and you want to take a full backup every Sunday and T-logs every 15 minutes. And disaster strikes and now you need to restore back to point in time. Right. So traditionally, I would have to go through a multi-hour full restore from last Sunday, and then I have to apply many days worth of T-logs to restore back to Friday at 4:14. And what happens when you have your boss breathing down your neck, or in this case, well, in either case, pestering you for something because you got to get that data back as fast as possible. Now imagine a world where you have application consistent snapshots at your disposal, T-SQL snapshot backups. So you know what? I can now, instead of having to take a full backup that takes many hours just once a week, maybe I'm also supplementing my existing backup strategy with application consistent snapshot backups that are taken once a night, perhaps. So now I only have to use an application consistent snapshot to restore to Friday at midnight. That could be nearly instantaneous depending on your underlying storage. And then now I only have to do Friday's worth of T-logs to catch back up. That decreases my recovery time dramatically. Again, your mileage may vary depending on who you're using for your storage, but for your very large multi-terabyte databases, this could be an interesting alternative to also further enhance your existing backup strategy. I am not advocating that you replace all of your backup strategy with, T-SQL snapshot backup, big and small. What I advocate for is a mixed approach where you're using multiple tools, because because this is a backup operation, you can do it as a copy only with the application consistent snapshot backups, and still take your traditional full backups on Sunday if you want to still have that level of comfort, because this is tried and true. So you can absolutely do a mix and match here. Okay. So with that, we are at time. So I'm going to leave you with some parting thoughts, and then I will go through some questions here. So just to recap, we talked a bit about backup internals. I introduced you to like the backup threads, the readers and writers, and the backup buffers, and how they all kind of play together and work in conjunction with one another. And then we saw a little bit about different data transfer tunables and some demo around, playing around with buffer count, max transfer size, increasing the number of disks and stuff. And then I talked a little bit about it, introduced you to QAT and some of the benefits there in SQL Server 2022. And you got a little bit of a bonus with an introduction to T-SQL snapshot backup. Just remember though that, in the end, there's all these different tunables that are available to us. They can improve your backups and accelerate them, but there is that diminishing rate of return, and we must be mindful of the balancing act still between everything else that may be going on either on our single SQL server or maybe downstream at our backup target, because there are many SQL servers that could be backing up simultaneously. As promised, there's a ton of different resource slides here. Again, all of this is available on github.com/SQLBeck. And with that, let's go look at the chat and see what questions there are.
Got a couple of good questions on here. Do you know for the T-SQL snapshot, I can't speak today. For the T-SQL snapshot, do you know if that would be supported if running on VMware vVols?
Absolutely, yes. Very, very simple answer. But yes, I talk about that day in and day out. vVols are awesome,
Cool.
especially on Pure. I don't know about other vendors, but on Pure, they're awesome.
Pure's the only storage I get behind, but I'm not going to market for you guys. I don't have to.
I'm a little biased.
Uh,
Let's see. Regarding backup writers, could you have two separate file paths set up that point to the same location to trick SQL Server into thinking there were multiple volumes? Or is the number based solely on the, so if you had two separate file paths set up to, no, SQL Server actually is, knows, so like if, for example, it's the D drive, but like, data 1, data 2, data 3, data 4, SQL Server will know that it's actually still one singular volume. Now, if data 1, data 2, data 3, and data 4 were separate mount points, those mount points, of course, are tied to individual volumes. But no, you cannot trick SQL Server with multiple folders and thinking that it's multiple volumes. SQL Server, if I remember correctly, underneath the covers, actually relies on the Windows OS to get that information, and the Windows OS knows that it's just one volume. So,
awesome. If
great
anybody's
questions.
got,
Did I miss any questions earlier?
I think we're good. If anybody's got any questions, feel
Hi,
free.
Andy. This is Haripriya. That was
Hey,
a
Haripriya.
that was a great session. Thank you so much. I have a couple questions.
Sure.
So first thing, I think it's a simple question. I wanted to find out what stun means. I have no clue about that.
So what I mean by a stun, so that means all I/O is paused to the underlying database. You cannot read from it and you cannot write to it. So all I/O is paused.
Okay, so that's
It's
what
the
stun means.
Yeah, it's the equivalent of being whacked in the head with a baseball bat. You just kind of for a second.
Okay, thank you. And the other one is the Intel QAT that you mentioned.
Yes.
So that comes by default in 22. For the backups, we don't have to do anything at all.
No, you do have to jump through a few hoops in order to turn it on. That's, I don't have the time to cover that here, but there's some blog posts and documentation about that. And it also depends on whether you're doing hardware acceleration or software acceleration.
Yeah, if you're going to do hardware acceleration, you have to have a particular piece of hardware available for it to offload that compression to. And most administrators haven't heard of it yet. So if this is something that can help you, talk to them because they may need to actually buy it and shove it in the equipment so that you can use it.
Oh, okay. Oh, so that needs some effort then. Okay.
A little bit of
It's
effort, yes.
it's minor, but it's there. Yeah.
Okay. Great. Thank you. And a great session as always, Andy. Thank you.
Thank you.
Yeah.
Any other questions or comments? And
That's
if there are no questions or comments, well, if I could ask for a little bit of feedback in the chat, please. Just give me a quick +1 or -1 or 0 if this session did or did not meet your expectations or, helped you out or if you found it useful, right? It's all anonymous, or not really anonymous, but, I'm not going to look at names, but I just want to get a sense of, hey, was this worth your time? Did it work for you? I hope this was, something constructive and you learned at least one little cool tidbit. So.
Oh, this is awesome. I spend my days performance tuning of, some pretty big machines. The stuff that you discussed here, these are things I do day in and day out, and a seemingly minor change can take your backup time and cut it in half. And, for a single database, it's 5, 10 gigs. Okay, a couple seconds. You back up a 100 terabyte monster, cut it in half. That matters.
Yep.
That's the difference between a daily backup, a weekly backup, or in some cases, a monthly backup. Makes a huge difference. So this is awesome.
Yep, I've had cases where I remember one particular job. I only had 12 SQL Server instances, but each SQL Server instance had a couple of thousand databases on them, each of varying sizes. Some of them were tiny, some of them were huge. And back in that day, I only had really crappy spinning disk SAN to write to, and it was a hand-me-down SAN as my backup target. So I could not run even though I had a decent-sized backup window, I could not write everything to that backup target simultaneously across those 12 SQL Server instances because it would crash that SAN. So I actually had to work out a lot of math and work with these different tunables to be able to maximize my time window and not overwhelm the SAN as well. So it was actually a lot of calculus and algebra to try and figure out, okay, and I wrote a bunch of code in order to try and orchestrate and do this to not overwhelm the SAN. The nice thing is that I did have decent maintenance windows, so I could utilize, all the resources, so I could crank up, the number of CPU threads. I could do things in parallel up until bandwidth wound up being my bottleneck and incoming bandwidth into that old school SAN. But like I didn't have to worry about, memory utilization. I can crank up buffer count, for example. But as we all saw, again, diminishing rate of returns. I can't set buffer count to 5,000 and just magically increase, my backup to light speed. There's always that, where's that kind of sweet spot where I'm going to get a really good rate of return. It may not be the most perfect, but it's still, hey, 80%, 90%, but am I going to ever reach 99? Yeah, probably not,
Outstanding
So
stuff.
thank you all for the feedback in the chat. I appreciate appreciate all that.
Yeah, and if you're watching this on YouTube after the fact, you've got his contact info right there. Do not hesitate to reach out to him or us. We love this stuff. We're total nerds with this stuff. We just want to help. If you like this session, if you have any follow-up topics that you want to see presented here, let us know. We are weird in that we'll actually create presentations just for you. If we can solve answers or solve problems and answer questions, we're happy to do so. So let us know. Again, if you're watching this after the fact, thank you for taking the time out of your day. If you're watching this live, even better. Fantastic. Thank you very much, and we'll see you on the next one.
Take care, everyone. Have a great one. Cheers.